Hey physics babies! Welcome to Physics Pandemic Education. This is episode 4. Today we are going to get started with Unit 5, Lesson 2, and we're talking about electric fields. Should be good. All right, so this is Unit 5, Lesson 2, and we're talking about electric fields. Our objective for the day is that by the end of the day, you will be able to model the electric field using field lines, as well as calculate the electric field strength on a test charge or a charge in the field. So, demonstrations. Unfortunately, I'm not able to do any demonstrations given the quarantine situation that we all find ourselves in. But I have a few YouTube links that I'll put in Google Classroom. Please, when you have a second, go and watch these links. Electric fields can be a little tricky because we can't see them, but through these demonstrations, you're able to kind of see what they look like. So it's definitely worth it. Take the time, go watch a couple videos, okay? So, charged objects have invisible properties that we call an electric field. The electric field shows the electrical force that allows it to do work on other charged particles. So, like I said, we can't actually see it, so we like to draw it so we can understand what's going on and help make predictions. But the key about an electric field is that it shows electric force, and the electric field allows it to do work on other charged particles. Two things happening. So we figure out the direction of our electric field lines based on what would happen if we put a positive test charge near the object. So we have a charged object, and we think, if I put a positive charge near it, what direction would the electric force point? So let's say our object is positively charged, and in the slideshow, you can see it's that larger pink charge. If I put a positive charge, the little small charge, near the positive object, what's going to happen? Are the two objects going to attract each other, or are they going to repel each other? Well, like charges repel each other, right? So as you can see, we've got two arrows pointing outward from each of these charges. My test charge is going to the right, and my positive charged object has an arrow pointing to the left. Well, an electric field doesn't just exist in one direction. They actually point everywhere. So we draw our field lines radiating outward from our positive object, okay? We figured out that outward direction because if I put a positive test charge anywhere around this charge, right, it's gonna cause a little arrow to point away from it, okay? The direction the arrows point is honestly the biggest part of this, all right? Whenever you have a positive charged object, you need to remember that the arrows point away from the charge. So what about if our object is negative? Again, we think about putting a positive charge near it. What's going to happen with our negative object and that positive test charge? Are they going to attract each other, or are they going to repel? Well, opposite charges attract each other, right? So you can see we've got arrows pointing towards the two charges. So we draw our field lines radiating towards a negative object. So for a positive object, our field lines point away from the charge. For a negatively charged object, the field lines point towards it. And again, they have to exist in all directions, not just one. So what does the electric field look like if we have more than just one charged object? This is where it might get a little tricky. So we've got three different situations. We've got a positive and a negative. We've got two negatives, and we've got a negative and a positive. Pause the video, and I want you to write down 5 things, quick little jotted things that you notice about these 3 pictures. Okay, so coming back to it, you should have noticed that with a positively charged object, the field lines are always pointing away from it. You should have noticed that if the object has a negative charge, the field lines are always pointing towards it. Another thing I hope you noticed is that the field lines can never cross. Do we see how in between the two objects, the two charges, for each of these cases, the field lines curve so that they can't actually crisscross each other? Looking at this example of the positive and the negative, the field lines from the positive point towards the negative, but I can't have the two field lines crossing, so instead they curve. Same with our negative and negative. All the field lines still point towards the negative charges, but in between, they get this crisscross, so instead they have to curve to avoid each other. On the far right, we've got the two positive charges. And again, they're all pointing outwards, but instead of crisscrossing, they have to curve away from each other. Now, closer lines means that we have a stronger field. Basically, the closer you get to the charge, the stronger the field's going to be because you're closer to more of those electric field lines. If I were to place myself right here, say, oops. If I were to place myself right here, I am super close to two field lines versus if I point myself over here, I'm a lot farther away from both of those field lines. So I experience a weaker electric field. Okay. So how strong is the electric field? There's a pretty straightforward calculation. Our electric field strength, which we use a capital E for, is measured in newtons per coulomb. Okay, so we take F sub E, which is the force, the electric force on the test particle, and we divide it by the charge of the test particle. Okay, we give that Q sub naught to be the charge of the test particle as opposed to the charge of the object in question. So we've got an example. We've got a positive test charge of 1.0 times 10 to the negative 6 coulombs, and it's in an electric field that exerts a force of 2 times 10 to the negative 4 newtons. We want to know what the magnitude of the electric field is at the location of the test charge. So let's move in. Hold on, give me a second. We can get our document camera up and running. Okay. So, our example. We've got a positive test charge. So we're going to give it Q naught because it is the test charge. That is 1.0 times 10 to the negative 6 coulombs. And it's in a field that's exerting an electric force, Fe, of 2.0 times 10 to the negative 4 newtons. And we want to know the magnitude of the electric field at that location. So we want to know E. So to find E, we're just going to say E equals F sub E over Q naught, which is 2.0 times 10 to the negative 4 divided by 1.0 times 10 to the negative 6. Okay. 2.0 times 10 e to the negative 4. We're dividing all that by 1.0 times 10 to the negative 6. I get, oh, sorry, I didn't realize you probably couldn't see that. I'm getting 200. 200. What's our unit for this? Newtons per coulomb. Easy peasy. So that was the only real example we were going to do. If we were in class, you would move on and do these guided practice problems with a partner, but instead you can do them with me. So this worksheet is on the Google Classroom. You are free to just, copy. What I would do if I were you is just kind of title at the top of your notebook, Unit 5, Lesson 2, Electric Fields. And then, you know, problem 1, you don't need to write out all of the directions, but problem 1, and then show your work. So we're going to sketch the field lines around a single positive charge. So we're going to draw my charge. It's positive. Make sure you mark all of the charges when you draw them so you know, looking back at it, was it positive or was it negative? So I have to think, if I put a little positive charge in here, what's going to happen? They're going to be repelling each other. So I know my field lines are all going to point outwards. Look at that. Easy peasy. Okay. Number 2, we're going to sketch our field lines around a single negative charge. So one charge that's negative. Here we go. Draw that in. And I need to think, if I put a positive charge next to it, what's going to happen? Well, it's going to be attracted. It's going to want to move that way, right, towards that positive charge. So all of my field lines have to point towards that negative charge. If you're struggling to remember both of these, maybe just remember one and then know that the other is the opposite. Just an idea. All right. Number 3, we've got the field lines for a positive charge that's next to a negative charge. So I have to draw 2 charges. One's going to be positive and one's going to be negative. So I know my positive the positive and the negative are attracted to each other. So I've got one field line taking the positive towards the negative. I know that all of these field lines from the positive to the negative want to go towards that negative. So they start out angling out from my positive charge, but then they curve in towards the negative. On this outside of my charge, we're too far away from the negative to really curve in, so we're just going to point outwards. Same thing over here. We're too far away on the negative to be kind of pulling from the positive, so it's just going to point inwards. A good rule of thumb whenever you're doing your charges, right, is that you've got lines coming from the top and bottom, from the left and right, and then hit all of these little in-betweens. Kind of looks like a sun. How fun. Okay, so you should have 1, 2, 3, 4, 5, 6. Shoot for 8 field lines whenever you draw a charge. So it's kind of like the unwritten rule. All right. Now we're going to sketch the field lines of 2 positive charges that are next to each other. So positive, positive. I know field lines point away from positive charges. So I'm going to start with the easy part, which is the outside, because I know on the outside for each of these charges, they're too far away from each other to be impacted by that other charge. Now, I need to draw a few more field lines for each of these, and I know they cannot crisscross. Because they cannot crisscross, I need to make them curve. And then for this last one, I'm going to make this one go up and then this one go down. Easy peasy. Okay. Key takeaways from this: please make sure that your field lines do not cross, and make sure they point away from positive charges towards negative charges. All right. Last little problem to do together. We've got a positive chest charge of 4 times 10 to the negative 6 coulombs. So Q naught equals 4.0 times 10 to the negative 6 coulombs. Notice that the first step is always to write down your givens. It's like some things just don't change, pandemic or not. All right, it's in an electric field that's exerting a force, F for force, E, of 2.3 times 10 to the negative 4 newtons. We want to know the magnitude of the field at the location of the charge. I gave the answer. Let's double check that we can get there, okay? I know that E equals the force divided by the charge. So that's going to be 2.3 times 10 to the negative 4 divided by 4.0 times 10 to the negative 6. Okay. So we've got 2.3 times 10 to the negative 4 divided by 4.0 times, oops, that's not what I wanted, times 10 to the negative 6. 57.5. My units are going to be newtons, per coulomb. Okay, so if you forget about your units, just remember, what do we measure force in? Newtons. What do we measure charge in? Coulombs. We keep those units the same all the way at the end. All right, easy peasy. So that's it for our lesson today. For your exit ticket, I actually am going to ask you to do the independent practice problems. Do them on a scrap sheet of paper, take a picture, and then you can either submit it via the Google Classroom or you can email me. I'd prefer it if you could submit it to the Google Classroom, but if you're unable to do so, send me an email with it, okay? If you have any questions or concerns, feel free to come to office hours during those Zoom meetings that are being held from 2 to 3 every day. Stop by to ask questions or just to say hi. That's it. I love you guys so, so much, and I hope you're all doing well, and I hope I can see you in our meetings. Bye.